This chapter deals with standing waves on a string. I have made a video explaining the phenomenon of standing waves. The link is on D2L, so you should have a look at that. A couple of precursors to the standing waves that you're going to need to know is about traveling waves in general. And chapter 15 actually deals in great detail of traveling waves. But what we need for our purposes here is the relationship between speed, wavelength, and frequency of a wave. So this is the speed of a wave. This is any kind of wave, sound wave, water wave, wave on a string, electromagnetic wave. This is always true. So speed of a wave. Lambda is called the wavelength. This would be in meters. And F, as usual, we have known that this is frequency in hertz. Okay, so if you're looking at a wave, like a water wave, and you take a snapshot in time so that you're looking at the displacement of the wave as a function of position, that's what wavelength is. It's peak to peak to distance. Okay, so that's one way to represent a wave. Now, waves have three properties. They've got the displacement up and down. So imagine a cork on a water wave, and the cork goes up and down and up and down as the wave passes in space from, say, right to left. So you can graph the wave as a function of position, like this would be a snapshot when t is fixed. So that's just like taking a picture. Or you could just look at the cork on the wave and fix the position. It's called a history. And you let x be constant. So you just look at the cork in one position, and then this would be a function of time. And if it's a function of time, peak to peak is now period. So it depends on what you're graphing and what you're looking at, of whether or not the peak to peak is period, that goes with time. That's the time for the cork to go up and down as the wave goes by, or wavelength, which is peak to peak distance if you take a snapshot picture of that wave. Okay, now we're not going to do water waves, but we're going to do waves on a string. And so the equation that you need that quantifies that speed is the tension in the string, F sub t, and what's called the linear mass density. So Ft is a force, it's the tension in the string. If you pull a string tighter, the speed goes up. So this is in newtons. And mu is called the mass density. That's how fat the string is. And this is going to be in kilograms per meter. Now beware of, often they're going to give you grams per meter. You have to convert. So the definition of the mass density is the mass of the string divided by the length of the string. And just make sure that mass is in kilograms before you use this equation, or it's not going to work out. Okay, and so this is speed in meters per second. And so that does equal, this V equals lambda F. It's the same V if it's on a string. So those are equal to each other for a string only, not a water wave or a light wave or sound wave. This is only for a string. And that's what we're going to consider in this chapter. Okay, now the video that I made on standing waves will show you how it works, what's going on. It requires interference of waves. It requires waves traveling both to the right and to the left and interfering. And there will be questions on your mastering physics that deal with this kind of interference. So you'll have little examples where, say you have a pulse, a square pulse that's traveling along on a string. Now, this is pretty theoretical because it's pretty hard to get a string to look like that. However, if someone created that pulse traveling to the right, and then someone created a pulse, exactly the same pulse traveling to the left, when these strings meet up, you're gonna get a pulse twice the height. And that's called constructive interference. And then they'll pass by each other. This is the amazing thing. Then they'll pass by each other as though they never even saw each other. And they will carry on unperturbed in their respective directions. So this is called constructive interference. And you simply add the two waves together and you get a peak twice the height. So if this height were h and this were h, this would be 2 times h when they meet. And then they'd go on and they'd be h and h again. Now, it is possible for you to completely cancel out pulses if one were going up and another were coming along down. Well, when they happen to meet, you get nothing. They would cancel each other out. But then later on, they would just pass by as though they were never there. So the up one would keep going, the down one would keep going. This would be destructive interference. And that is the principle behind standing waves. And the video that I did for that will show you how that works. And then the normal modes of oscillation for our strings, the PowerPoints do a good job of laying this out. The equations that you need for standing waves on a string are that the frequency of the mode, the normal mode, is a multiple of the fundamental frequency that looks like that. And so that's the only equations that you need to do all the standing wave questions. And there's some good videos on Mastering Physics about this and some very good pictures in your PowerPoint slide. So that's all you need for this.